Hello and welcome to the lecture on linear motion for my wonderful students in Abu Dhabi. And this lecture is going to be closely related to the test on linear motion. And the test will be closely related to the lecture. What came first, the lecture or the test? Either way, if you know this lecture, you're going to be in pretty good stead with the test. So let's begin. Linear motion is precisely what it describes. It's straight line motion. And the first thing you need to do in straight line motion is to understand relative motion. Here are some speeds of various items, both in miles per hour and kilometers per hour. A very good sprinter is running 25 miles an hour. That's it. 11 meters per second. 40 kilometers per hour. That's it. You would think that they would be much faster than that. Look at the tsunami trying to outrun the tsunami or outrun a batted baseball. Here we have a cheetah. It's the fastest land animal over a distance of less than 500 meters, and it can achieve peak speeds of 100 kilometers per hour. So everything is relative. If you're on the E10 or E22 or some other big road and you're neck and neck with another car, what's your speed relative to the car that's going the same speed? Let's say you're both going 120 kilometers per hour. Well, your speed relative to the car is 0. Relative to the ground, your speed is 120 kilometers per hour. Now, let's say you're in a big bus, and the bus is moving 120 kilometers per hour, and you walk to the back of the bus 5 kilometers per hour. Well, what's your speed relative to the bus? 5 kilometers per hour. What's your speed relative to the road? Well, 120 miles per hour minus the 5 miles per hour because you're going in a different direction. So your speed relative to the road would be 115 kilometers per hour. So everything is relative. All speed is relative. If you're in the back of the bus and you walk to the front of the bus at 5 kilometers per hour, then your speed is relative to the road is 125 kilometers per hour. Now, another thing that you should be aware of, and that's average speed. Average speed is one of the most one of the easiest things to calculate in this type of physics. It's simply total distance covered divided by total time. If I'm driving to Dubai, well, it may take me an hour to get there. So let's say it's 100 kilometers and it takes me an hour to get there. Well, how far away is it? These are questions that are based on average velocity. But the question is this: were you always going the same speed? If you look down at your speed and you see I'm going 100 kilometers per hour, or I'm going 40 miles per hour, or I'm going 30 kilometers per hour. These are instantaneous speeds. You weren't going the same instantaneous speed the entire way. So in order to get your average velocity, you took the total distance and divided it by the total time. So if it's 100 kilometers and you took 1 hour to get there, your average velocity was 100 kilometers per hour. Now let's talk about something that oftentimes students get confused with, and that is the concept of the tailwind versus the headwind. Now, maybe international students don't get as confused with this because they've taken planes quite often, but if you have a tailwind, you're actually increasing the speed of the plane by adding the two vectors, by adding the vector of the speed of the plane plus adding the vector of the wind, and you'll get the total ground speed. Now, or the total speed relative to the ground. If you have a headwind, that's going to subtract from that and decrease the ground speed, because the ground speed, again, is the speed the plane is going relative to the ground. So velocity is a vector quantity, so you can add vectors or subtract them or add negative ones, such as in this case of wind speed and headwinds and tailwinds and ground speed and etc. So next, let's look at a problem. Navigating an airplane. An airplane flies at 200 kilometers per hour relative to the air. What is the velocity of the plane relative to the ground if it flies during the following wind conditions? Now keep in mind that velocity is a vector. Speed is scalar. So the velocity of the plane would be a speed plus a direction. Therefore, you can add or subtract these particular vectors. So you have a 50 kilometer per hour tailwind. What does that mean? Well, that means that you have a wind blowing at from the back of the plane to the front of the plane. So you can add those vectors. Now, the airspeed is 200 kilometers per hour. The tailwind is 50 kilometers per hour. Now, the speed relative to the air, again, is 200 kilometers per hour. But I want to know what is the ground speed? What is the actual velocity of the plane relative to the ground? Well, what you do is you simply add the vectors. 200 kilometers per hour plus 50 kilometers per hour, or a positive 200 kilometers per hour plus a positive 50 kilometers per hour equals a positive 250 kilometers per hour. If you assume that the direction that the plane is heading is positive, a positive vector. Always important to put the positive vectors in. So this is right out of the book, and the only criticism that I would give is that there should be a plus sign in front of the 200 kilometers per hour and a plus sign, other than the sign for operation, in front of the 50 kilometers per hour. Now, I have a 50 kilometer per hour headwind. Now, remember, the 200 kilometers per hour, because we're assuming that the front of the plane, or the direction of the plane is positive. So it would be positive 200 kilometers per hour plus a negative, or 50 kilometers per hour. It's not particularly well done that you would say minus. We don't subtract vectors. We add them. And it would be more appropriate to say plus 200 kilometers per hour plus a negative 50 kilometers per hour would equal 150 kilometers per hour. But you get their point, and their point is fine. But just learn more appropriate language in dealing with vectors. Here I have a rock, and believe it or not, that rock has a odometer on it, or a speedometer on it, or some other device that allows you to track the motion of the rock. Now, from the lines that are vertical above the rock, you can clearly see that the rock is falling in what I call a gravity well. In other words, in the presence of gravity. In other words, it's going down towards Earth. And it says, the problem says, if a falling rock were somehow equipped with a speedometer, in this particular case, in each succeeding second of fall, its reading would increase by the same amount, 10 meters per second. Table 4.2, you can look in your book, shows the speed we would read at various seconds of fall. Now, where does the 10 meters per second come from? The 10 meters per second actually comes from the fact that the acceleration due to gravity is 10 meters per second squared, or 10 meters per second. It increases or decreases every second. So if the rock is falling, you're going to say that the velocity will increase 10 meters per second every second. 10 meters per second every second. If I threw the rock upward, its velocity would decrease 10 meters per second every second. So, very important when you talk about this, that you have to be aware of how objects fall or behave in space when falling in a gravity well, meaning near a planet. Not just falling, but near a planet. Now, here I have the table 4.2. Can you predict, we're assuming that the rock is falling from rest. Can you predict and actually come up with the equation for each successive second on this particular table? Now, the first one would be 0. It is going to fall 0 meters per second because it's at rest when it's released. So now, if it's at rest when it's released and it's going to fall at a rate of 9.8 or 10 meters per second squared, what will be the speed after each successive second? What will be the speed after each successive second? That's the question. You can see that the velocity will be 10 meters per second, and it will increase 10 meters per second for every succeeding second. Now, what would the equation be? Well, we know that g is the constant. So, the two variables would be velocity and time. What is the relationship between those two variables? What is the relationship between velocity and time? In other words, as time increases, what happens to the velocity? As velocity increases, what happens to time? Well, we see that velocity and time are directly proportional. They're directly proportional, and they are indeed linear. Look at it says 10, 20, 30, 40, 50, 1, 2, 3, 4, 5. Therefore, the equation would be V equals G10. Well, we know that G is 10 by graphing the data because G is the slope of the line. Because the slope of a linear line is a quotient constant. In other words, the change in y over the change of x equals a constant. And if it's linear, then that constant equals a quotient. In this case, speed over time. Now, so what happens to the distance? What happens to the distance as the boulder goes down? What happens to the distance? How does that change? Well, we know that the velocity relative to time changes in a linear fashion. We know that it changes in a linear fashion relative to time. Now, relative to time, how does distance change? Relative to time, how does distance change? Now, it says, pretend that a rock falling is somehow equipped with an odometer. Odometer measures distance, odometer. The readings of distance fallen increase with time and are shown in table 4.3, which we'll see next, and that table will show precisely the same changes as the table did 4.2 relative to velocities. So let's look at that table, and as the as the distances are uncovered for each individual successive seconds, let's talk about how the equation might be written for distance versus time. Distance versus time. Now, remember one thing, that the velocity, the initial velocity is 0. That's a very important element of this exercise. Well, if the initial velocity is 0, then the relationship will be, what's changing? Well, time and distance. So how are time and distance changing? Remember, the acceleration is going to play the function of the constant. Again, it's no secret. It's falling in a gravity well, and that gravity well is governed by the acceleration due to gravity on this particular planet. We know that it's 10 meters per second squared. So how is it changing? Well, we know that the average velocity over the first second will be 5 meters per second. Well, all right, 5 meters per second. So let's see what that means. Starts at 0, it ends at 10 meters per second. We saw that in the last graph. So 1 second, 5 meters per second, 1 second will be 5. Now, what about 2 seconds? Well, let's see. 2 seconds, it would be 20 meters per second, and the average velocity 20 plus 0, the initial velocity, divided by 2 is going to be 10 meters per second. So in 10 meters per second, in 2 seconds, it's going to be 20 meters. So let's use that same idea to try and predict the next distance. Let's see if we can't predict the next distance. Here we go. Oh, 45. Now, does that make sense? Well, let's see. At the end of the third second, the boulder was going 30 meters per second. So 30 meters per second plus 0 divided by 2 would make it 15 meters per second. For 3 seconds, it would be 45 meters per second. Now, just remember, the initial velocity plus the final velocity divided by 2 can also be the average velocity. Average velocity is not only distance over time, total distance over total time equals average velocity. Average velocity also is the equation initial velocity plus final velocity divided by 2 also equals average velocity. Very, very important, especially for predicting the next one. So if that logic is correct, then after 4 seconds, it would be going 40 meters per second. The average velocity, therefore, would be 20 meters per second. 4 times 20 is 80. Let's see if that works. After 5 seconds, it would be 50. Half of that is 25. 25 times 5 is 125 meters per second. So it looks like the logic is starting to pay off. Now, look and see how this is increasing. It's going 5, 20, 45, 80. Well, it's kind of changing in a parabolic manner. In other words, distance is going to equal some kind of x squared idea. Well, what we're going to have to do after we finish filling in this chart is come up with a graph, and then let the graph decide Now, this is going to completely give away the whole idea of the equation, and much of this is done qualitatively. We know prior to problems that we've done that the equation is indeed going to be a square function. Distance is going to be a function of time squared. But what's important to note here, even though it's going to kind of give away the answer by saying that the distance will equal a square function, and in this case 1/2 g, which is the constant, and t is squared. So the relationship between d and t is direct, but it's also parabolic. So now, if we graph this, we will clearly see that it is indeed a parabolic equation. It is indeed a parabolic equation. So the graph that we see here is, if we used our algebra skills, we could determine that this graph is part of a equation that is parabolic in nature. So very important to understand the relationship between time and distance is parabolic. We're going to look at a few graphs coming up in a moment which will illustrate this point further. Not only that the distance time graph is linear relative to a constant velocity, but it is also parabolic as well. So let's see what all that means in the upcoming graphs. The following are graphs and tables that illustrate the point of the relationship between distance and time and velocity and time. In the first set of data, we are going to graph some data of position versus time. The x-axis is usually considered to be always time, the independent variable. And the y-axis is going to be position, or distance traveled. You can see that it is a straight line. And the reason it's a straight line is because the change in position relative to time is constant. Look at the slope. The slope is linear, and the change in position relative to the change in time is going to be the slope, and the slope of the entire line is constant. And as you know, the slope of a position time graph or distance time graph will be the velocity. In the next set of data, we have position versus time graph again, but with constant acceleration, meaning the position is changing in a different way. Remember, we saw on one of the last slides that when the change in position relative to time is parabolic, that means that acceleration is occurring. Now, the acceleration may be occurring because of gravity or because a car is accelerating, whatever the case may be. But this constant acceleration is a result of gravity or some other thing, or some other idea or understanding. Here I have something very similar to the acceleration due to gravity that we looked at before. A little bit different. But we see that the position is going to be at 0 at rest, and then at the end of the first second it's going to go 10 meters, and then 40 meters, and then 90 meters, and then 106 meters, and then 250 meters. The position versus time is going to be some form of parabolic function, some form of parabolic relationship between the two. Now, the next set of graphs we're going to look at are going to be velocity and time. Velocity versus time graphs. Now this one says time versus position, but actuality you should always say y versus x. Okay, here we have velocity time data, and we see that it's not increasing, not decreasing. It remains the same. So as the time increases, the velocity stays the same, and you get this horizontal line with a 0 slope. That means that there is no acceleration. If you have acceleration, or if the acceleration is in 0, you have this increased velocity, uniform increase of velocity, and you have an acceleration and something other than 0. And that's generally the type we're going to have. We're either going to have 0 or a positive acceleration that's uniform. In this next graph, it's going to emphasize an acceleration. An acceleration is change of velocity over change in time, and it's going to be change of velocity over change of time, constant slope. Now I have acceleration versus time, and we don't really look much at graphs, acceleration versus time, but in this particular case, this is really the only acceleration versus time graph we're going to have, and that is where you have a constant, a zero slope relative to an acceleration time graph. Acceleration versus time, even though it says time versus acceleration. It's usually y versus x, but this particular graph seems to put x versus y, but it's usually y versus x. That concludes the lecture. Good luck. Look at all the lectures. There's going to be several of them on the web, and expect daily quizzes. Thank you very much.